Welcome to CW 2.1. Today we'll be talking about the next chapter, and we're studying a pretty cool topic called combinatorics, which is essentially the study of counting. And it sounds pretty simple, but you're going to see how it's pretty complicated. So first, we got to recall this fact, the exclamation point right here, that's called a factorial. And you might have seen it before in an earlier math class. If not, that's okay. What it means is you multiply down all the way to 1. So this is 26, 25, 24, 23 times 22 times 21 times 20, dot, 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 all the way down to 1. So you can imagine it's a pretty massive number. And 21 factorial is going to be 21 times 20 times 19, dot, 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 all the way to 1. Now the first thing to realize is it'd be silly to multiply all these together, divide by all these together, because there's a whole bunch of things in common. Look at 21 down. These are all there, and they're in common, top and the bottom, which means we can effectively cross these out. So to make our work a little bit cleaner, we're going to do this. We're going to leave 21 factorial alone, and then this part, notice how I erased it? It was 20, 19, and so on. We're going to erase over here and make 21 into a factorial. So notice how I'm basically breaking this off and then leaving 21 factorial because that will continue down to 1. And now I'm just going to cross these out. Now my calculator, I'm going to type in that information and you're going to get this, 7,893,600. That's your answer. So next couple we'll do without a calculator. So I have 10 factorial. So that's 10 times 9 times 8 times 7 dot dot dot. At the bottom I have 2 factorial. Notice how that's just 2, because that's just 2 times 1. And then 8 factorial. So you should recognize that this 8 factorial, I can actually recreate that right here. I just want to make this 8 factorial, because that's going to cover 8, 7, 6, 5, and so on. Cross those out. I'm left with 90 over 2, which is 45. Now let's try it with an abstract expression here. So n plus 1 factorial over n factorial. The first thing to realize is what's actually happening when you're doing factorial. Like when we say 3 factorial, that's 3 times 2 times 1. Notice how every single time we're going down 1, right? Subtract 1, all the way to 1. So for this thing, what you want to do is recognize that this one is larger, right? N plus 1 is definitely bigger than n. And we're going to break that down using a factorial. N plus 1, you're going to subtract 1 and get n and leave it like that. I'll make it a little bit nicer actually, like that. And the bottom is going to be n factorial. Okay, now you're going to cross this out. And look at that. That's just n plus 1, and that's your answer. Let's try one more. Notice that this is the bigger one. So you always want to break down the larger one. So you get n plus 2 times n plus 1 times n factorial. And I'm stopping at n, not because that's where I stopped here. It's because of the bottom. It's n factorial on the bottom. Had this been n plus 1, I would have stopped right here. But notice how it's stopping here. So that's where I want to stop my number there. And now I can cross it out. And the answer is n squared plus 3n plus 2. So for questions like this, we'll put this note here. Your goal is to cross out the factorial symbol. That's always going to be your goal for questions like this. Okay, now that we've done that, we can try some more advanced examples here. Example 1. Next semester, you're planning to take 3 courses, English, Math, and Humanities. Based on these time blocks and highly recommended professors, there are 8 sections of math. Okay, let's highlight that. 8 sections of math, 5 English, for humanities. Now here's a kicker. We're only selecting 3 of them. So 3 courses. And it's wondering how many ways can I pick these 3 courses. So 8 math, 5 English, 4 humanities. So you can imagine there are going to be many possibilities. Now the way we're going to do it, I call it slots. The formal name is called the fundamental counting principle. But essentially, you're going to draw 3 slots like this. 1 slot for each category. So that's math, English, and humanities. And what the counting principle says is all you have to do is fill in the options in each slot. So there are 8 sections of math, 5 English, 4 humanities, and you multiply it, and that's going to count up every single possibility. So there are 160 schedules possible. So pretty straightforward, and it's a very, very helpful principle. So if I want to try it here, you're taking you're taking a multiple choice test that has 10 questions, which means there can be 10 slots. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Each of the questions has 4 answer choices with 1 correct answer. If you select one of these 4 choices for each question, leave nothing blank, how many ways can you answer the question? So it's like saying you have a 10 question test. How many possibilities are there for answering this test? Well, in the first question, you have 4 choices. Next one, 4, 4. So it's all just 4. That's 4 to the 10th power, which is 1,048,576. Let's try another one. Telephone numbers. So telephone number, there's a 3-digit area code, so let's write 1, 2, 3. Then a 7-digit local telephone number, 1, 2, 3, 1, 2, 3, 4. And this is true, right? Because we have 808 and whatever your number would be. It says area codes and local telephone numbers cannot begin with 0 or 1. Okay, that's important. Okay, it cannot begin with 0 or 1. So what I'm going to do is I'm going to note I can't have 0 or 1 here or here. How many numbers are possible? So I have 8 choices here. Recall that 0 to 9, that's actually 10 numbers, right? 1 to 9 is 9, and include 0, that's 10. And this is important. The rest of the slots, 1, 2, 3, 4, 5, 6, 7, 8, you have 10 options because you can pick whatever you want. All we do is note that these are like the special ones. Those are the restrictions. So for a question like that, you always want to start with the restrictions there. So that's going to be 64 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that's how many telephone numbers can happen under these restrictions. Okay, here's our last example. It says using the formula for permutations. So basically, there's another way to do questions using a formula, but the formula is kind of limiting. The formula looks like this. NPR, and it's n factorial over n minus r factorial. This is called the permutation formula. And it's not super useful. I just teach it because you need it to do the next chapter, but we will use it a couple times just to see that it works. But it's kind of limiting. The permutation formula, it only works when order matters. And the second thing is your elements can't repeat. So that means it couldn't work in a question like this because your elements are repeating, meaning like I could use 9 multiple times or 8 multiple times because the phone number could be 888, 888, 8888. In a problem like this, you couldn't use this formula. So that's why this formula is not super like helpful in lots of problems, but you're going to see that it does help in very specific kinds of problems. So for example, if the problem was just straight up evaluate this right here, 7p3, you would just say, well, that's 7 factorial over 7 minus 3 factorial, 7 factorial over 4 factorial, and we can reduce that. That'd be 7 times 6 times 5 times 4 factorial over 4 factorial, and that would be 30 times 7, which is 210. Right, so if you ever see this notation, that's what it means. Apply your formula right here. And for this question, you're going to see it actually does work. It says you and 19 of your friends, let's just highlight that, are going to form a consulting firm. The group needs to choose 3 officers, CEO, a OM, a treasurer, and how many ways can those offices be filled? So using the formula, so I'll write that right here. Notice how this actually does fit my restrictions. The elements aren't repeating because you can't use a friend more than one time, meaning one friend can't fill all 3 of these roles. And the order does matter. Like it matters who's the CEO versus who's your operating manager versus your treasurer. So because of these conditions, we actually can use our formula. The way it works in word problems is this is like your total elements, and your R is like your choosing number. So in this one, this would be 20 because there are 20 total people, and there are 3 positions, so 20p3. So 20 factorial over 20 minus 3 factorial, which is 20 factorial over 17 factorial. And I can break this down here. At this point, you need a calculator. That would be 6,840 ways. That's how many ways we could fill these positions. Now you might notice that this method isn't really necessary here because you could use slots. So let's put a note here. You could use your slots, but you get the exact same thing. Right? You have 3 positions, CEO, OM, treasurer. You just gotta be a little careful because if you're filling the CEO, you can choose anybody. But the next one is gonna be 19. And that's because you've already used one person. One person's filling here, which means your treasurer is going to be 18. Times it all together, exact same answer. Okay, now I'm going to film a second part. Once you are done with the practice problems below, I want you to watch the second part of the video. Okay, so pause it here, finish the work, and then unpause it once you're ready. Now that you finished that worksheet, the worksheet kind of covers basic problems. These are going to be more advanced. So let's try it. How many 5-digit numbers are there? So for 5 digits, we're going to put 1, 2, 3, 4, 5. And each slot, we're going to think about what can be there. Now, if it's a number, that would mean you can't have 0 at the front. So for example, 10,000 is a 5-digit number. We can't have 0 at the beginning because that would no longer be a 5-digit number, which means there are only 9 choices here. The rest are 10 because you can pick whatever you want, which means in total, there are 90,000 5-digit numbers. Now, next part, how many contain no 4s? Well, this is pretty similar, right? The beginning still can't have 0, except now they all can't have 4, which means it's 8, 9, 9, 9, 9, which would be 52,488. Here's the part that's really hard. It says, how many 5-digit numbers are there that contain at least 1 4? And you want to highlight this at least 1 4. That's actually really complicated because that would mean there are multiple things happening. Case 1 could be you have 1 4 So for example, like 14,231, every number like that. There's case 2, which could be 2 4s. So for example, 44,231. Case 3, you have 3 4s. So for example, 44,431, and so on, right? All the way to 5. So notice how this would be pretty complicated to do each of these. And you could do it. Some people do it that way, and that's fine. But there is a better way. What we're going to do is look at A and look at B. A represents every single possible 5-digit number. B represents every single 5-digit number in which there are no 4s. So what we're going to do is subtract them. We're going to do 90,000 minus 52,488. That's going to give you 37,512. And that's the answer. Now take a minute to think about that. This is all. This is a situation where there are none. When you subtract that, that's going to give you at least 1. Because if you remove everything with no 4s, what must be left from the whole group is everything with at least a 4. That's a very profound concept, so you're really going to want to highlight that in your notes. That's going to be a big thing as we work in this chapter. Okay, let's try another one. All right, so the boys soccer team contains 12 seniors, 9 juniors, 3 sophomores, and 1 freshman. They're going to stand in line for a group photo. How many lines can be formed if there are no restrictions where the players can stand? So that would mean everybody can stand anywhere. So if you imagine you placing them, you'd have 25 choices, 24, 23, 22, all the way down, which is essentially 25 factorial. That's a massive number, so we'll just circle that and leave it like that. Now it says all the seniors must stand together, meaning everyone can be everywhere except for your 12 seniors. These people have to be together. So what you're going to do is called the one-person method. You're going to think of the seniors, these seniors, as one person. Okay, so imagine you push them together, one person. Now think of it as, well, how many ways can I arrange our people left over? So I have one person here, 9, 3, and 1. So 9 plus 3 is 12, 13, 14. So that would be 14 factorial. So that's every single way I can rearrange 14 people. Now we consider what's left. What I haven't done is taken these seniors and moved them around amongst each other. So the seniors here can move around amongst themselves. And they can move around in 12 factorial ways. And that's the answer here. Let's try again. The 2 Coles must stand next to each other. So this is saying that there are 2 boys in here both named Cole. And this was true a couple years ago. So get rid of this. What we're going to do here is say the 2 Coles equal 1 person. So how many people total are there now? Well, there would be 24 people and 24 factorial ways to arrange them. But now we account for the Coles moving, so multiply it by 2 factorial. And again, that's because the Coles can switch. Now let's try on this last one. All 12 seniors are together, which means the seniors are 1 person. The juniors are 1 person. The sophomores are 1 person. And of course, the freshman is 1 person. Which means, think of them as 4 theoretical people. And how many ways are there to arrange 4 people? Well, only 4 factorial. That's all the ways I can arrange these 4 people if they were 1 person. But now we're going to multiply it by the way they can move around. so they can move amongst themselves. So the seniors, there are 12 of them, so that's going to be 12 factorial, times the juniors, which is 9 factorial, times the sophomores, which is 3 factorial, times the freshmen, which is 1. And then there is your final answer, and you can leave it like that because that's a really big number. Okay, so I know this part's pretty complicated, so if you have any questions on this, make sure you email me so I can help you.